Hello everyone, welcome to the discussion on matrices from the ITJE examination point of view. Before we look at problems, let's quickly have a recap of this chapter. What did we see in this chapter? First, we began by looking at what was the definition of a matrix. We said that a matrix is nothing but a rectangular array of numbers. Moving on, we looked at different types of matrices. Now, what were the different types of matrices that we saw? Some of them were a square matrix which had equal number of rows and columns, a zero matrix which had zeros as all its entries. Then we had a row matrix which had just one row and let's say m columns, and the opposite of that, which is a column matrix which had just one column and let's say m rows. Then there were certain more interesting matrices such as the diagonal matrix, which was a square matrix with only the diagonal elements as non-zeros. A special kind of the diagonal matrix was the identity matrix, wherein all the diagonal elements were ones. Finally, we had something like the triangular matrices, either the upper triangular or the lower triangular matrix, wherein all the off-diagonal terms, either on the lower side of the diagonal or the upper side of the diagonal, were zeros. These were the main kinds of matrices that we looked at and moved on to matrix multiplication. First, we looked at multiplying a matrix with a scalar, and this was quite trivial. Then we moved on to the interesting matrix multiplication where two matrices were being multiplied. Now, it was not very trivial to multiply two matrices. We had to make sure that in order to multiply two matrices, certain conditions were satisfied. The most important condition was that when you were multiplying two matrices, the number of columns in the first matrix and the number of rows in the second matrix had to be same for them to be multiplied. Also, upon multiplying these two matrices, you get a resultant matrix whose number of rows was equal to the number of rows in the first matrix and number of columns was equal to the number of columns in the second matrix. We looked at properties of matrix multiplication, and one property which stood out was the fact that matrix multiplication was not commutative. This meant that AB was not always equal to BA. It might be or it might not be. So matrix multiplication was not always commutative. Then we looked at a very interesting topic, which was transpose of a matrix. If a matrix A has m rows and n columns, upon transposing it, we get a matrix with n rows and m columns. Based on the concept of transpose, we then looked at two different kinds of matrices, a symmetric matrix and a skew-symmetric matrix. If the transpose of A was equal to A itself, then A was a symmetric matrix. Or if the transpose of A was equal to the negative of A, then it was a skew-symmetric matrix. Finally, we looked at a concept which was the cofactor and adjoint of a matrix. Now, these were very interesting topics, and there was further other topics such as the inverse of a matrix and also solving system of linear equations. We look at these topics in detail in the chapter on determinants and solve problems from this more in the chapter on determinants rather than in this particular chapter on matrices. So it's now time to look at some problems from ITJE perspective from the chapter on matrices. Hello everyone, welcome to the discussion on matrices from ITJE examination point of view. In this first problem, they have given us three different matrices, X, Y and Z. They've said that matrices X and Y are 3 by 3 skew-symmetric matrices, whereas matrix Z is a 3 by 3 symmetric matrix. They've asked us to check which of the matrices given in the option are skew-symmetric matrices. Quite a straightforward problem, but a slightly lengthy one. So let's look at how to do this problem option by option. First, what have they given us? They've told us that matrix X and matrix Y are skew-symmetric. What does this mean? This means that X transpose is equal to minus X and Y transpose is equal to minus Y. They've told us in addition that Z is a symmetric matrix, and this means that Z transpose is equal to Z. Now let's look at option A. In option A, they've given us a matrix, and I'm going to call this matrix as matrix P. This is nothing but y cube z raised to 4 minus z raised to 4 y cube. We are asked to check the nature of this particular matrix. So let's take the transpose of it. So P transpose is the transpose of this given matrix. Now I'm going to make use of two different properties. The first property that I'm going to make use of is A plus B, the whole transpose, is nothing but A transpose plus B transpose. The next property that I'm going to make use of is AB, the whole transpose, is nothing but B transpose A transpose. So making use of these two different properties, the transpose of P simplifies to this particular form. Next, I am going to make use of another property, which is matrix A raised to n, the whole transpose, is nothing but matrix A transpose whole raised to n. Upon doing this, the transpose of P simplifies to this particular form. Now I'm going to make use of the given data.